Well, good morning. Today we're going to do the last new topic of the semester, which is on complex variables, complex numbers. Next time I'll spend the whole period doing review for the test, so make sure you take a look at the practice problems that are on D2L. See if you have any questions and bring them online. You can take your mute off and speak whenever you want then and today. Ask questions. Let me know if you can't see the board or whatever. It's easier probably to get here online than it is to come into class at 8 o'clock. Maybe that'll help my attendance this morning, huh? Do it from bed or something. All right. So it feels terrible talking to myself though. Anyway. Complex numbers are this, and we let I be a number such that I squared is equal to minus 1. We call it the imaginary unit. And since its square is 1, we'll write that I is the square root of minus 1. How can that be? What number times itself is minus 1? Well, there isn't a real number that way. We just make this up. We add it to the multiplication table. It's just a symbol, and when we multiply it by itself, we get minus 1. Turns out in industry and all sorts of scientific and engineering and other applications, imaginary numbers are real useful for getting to real results. So suppose I is the imaginary unit. Then, with that definition, a complex number is any number z equals a plus ib, or you can write bi, it doesn't matter, where a and b are real numbers. What are real numbers? They're all the numbers you come to know and love that can be written in decimal form, right? So if you write in decimal form, it's a real number. And if you take a real number plus I times another real number, we call that a complex number. These are real numbers, respectively called the real part and imaginary part of z. And we give some notation for that they might see in the literature. We won't use it too much, but we'll say A is the real part of z, and B is the imaginary part of z, like that. Some books just use one letter R or I. So the real part and the imaginary part are actually real numbers. The imaginary part, you think it has I in it. No, it's the part that multiplies the imaginary unit. Now we can do arithmetic with these. The addition of complex numbers is defined by, if I take a number a plus ib, here's a complex number, and I add it to another complex number, c plus id, I want it to follow the same kind of laws that I've grown to know and love from algebra, where you can add in any order and you can distribute and all that sort of thing. If I want to do that, I'll say you can regroup these, put c over here and take a plus c together, and collect ib and id together and factor out I, and we'll just define addition of complex numbers that way. Turns out this is really useful stuff, even though you say for a while, why am I doing this? And also we can do multiplication. We'll define it like this. If I take a plus ib, c plus id, two complex numbers, and multiply them together, I like them to follow the usual FOIL prescription, right? This times this plus this times this plus this times this plus this times this. So if I FOIL it out, I would get AC times that plus AID, and I can multiply in any order, so I call it IAD, plus this times this, IBC, plus this times this, BD times I squared. Well, I squared is -1. And then if you go back to addition and collect all the terms without I, you got AC minus BD, right? Plus a minus BD. And so we'll define multiplication by like this so that it obeys the distributive law, or the FOIL law. We'll say we're supposed to get AC minus BD for the real part of the number. And when we factor out I from these two parts, I multiplies AD plus BC. There's how we define multiplication. Now it obeys the usual distributive rules for multiplying these things out. What if we want to do subtractions? Well, we might, this let minus a complex number denote -1 times the number, right? We've got multiplication defined. And by the way, the real numbers are now a subset of the complex numbers, right? If you have a number like 5, you can think of it as 5 plus 0i. It's a complex number also. It just has 0 imaginary part, right? So that, and then we'll make this definition. Here's a complex number minus c plus complex number -1 plus 0i times minus c. How will we multiply that out? Well, we just distribute like we said we need to be able to do. We got minus a minus ib. And minus c just puts minus on each of these parts. And we just let that define subtraction. Then subtraction will obey the laws we know and love from real numbers. If we take a plus, we'll say that z1, one complex number, minus another complex number is going to be z1 plus minus the other complex number. Right? We'll define it that way. And then this is a plus ib for the first one. Plus minus this one is plus minus c minus id by our calculation here. And when you collect all these terms here, so this will define a plus ib, subtract the complex number c plus id, will mean the first one plus minus the second one, using multiplication. And then this one plus this one, we add a and minus c, and we get a minus c. And we take the I out of these two and get b minus d. And so subtraction is just a and b from the first number and minus c and minus d from the second number. So you just subtract the real parts and imaginary parts respectively. Okay, we need some examples. This is screaming for examples, right? Suppose I take 3 plus 2i, and I want to multiply it by 5 minus 3i, right? What do? All I have to do is FOIL. I can memorize that law if I want here, but it's easier just to FOIL. 3 times 5 is 15. Minus 3 times 3i is minus 9i. This times this, plus this times this is plus 10i. Plus this times this is 6 times I squared. All right. And now we collect the like terms again. I squared is minus 1. And so this is 15 minus 6 is 9. And minus 10i plus 10i is 1i, which we can write more simply just that 9 plus I. So there's the product of those two complex numbers. Okay? Very easy. The first part of this is all very straightforward. As usual, it gets harder and harder as we go, but I don't think you'll find this section too terribly difficult. Okay. Let's do some more things with these now. Need to move this back. We've done addition, subtraction, and multiplication. What else can we do? One thing is we can find the size of a complex number, the absolute value. We're going to do it in analogy to the real number. This is where it starts to get slightly harder. The absolute value, how can you take an absolute value of an imaginary number, right? By the way, if you have a number that's, maybe I should just say this in passing, like 3 plus 0i, you just say that's 3, that's a real number, it's a subset of the complex numbers. If you have a number that's like 0 plus 3i, we call this, if there's no real part, we call it a pure imaginary number. So these with 0 real part are called pure imaginary. And these with 0 imaginary part are called real numbers. And just your usual decimal numbers, because this just falls out. Just as a side note, the absolute value now of a complex number z equals a plus ib. How shall I do that? This has a really interesting motivation. It's an analogy to the real numbers. How do you define the absolute value of a real number? Think about it. You think of the real number line. If you take any number here like minus 4, right? Its absolute value is plus 4 is the distance to the 0 origin. And if I take the number plus 2, well, its absolute value is its distance to the origin. Absolute value of 2 is 2. Whichever side of the origin on you take the distance to the origin and call that the absolute value. Well, the complex numbers, we don't have a complex number line. For a good reason, is it's complicated, but in the study of fields of numbers, you can't order the complex numbers. It's not an ordered field. If you put them in some sort of order, then they violate their field properties. And so you can't make a complex number line like you can a real number line, where here each point, maybe this is minus pi, identifies a particular real number, right? You pick a point here and I say, oh, that corresponds to the real number 1. And there's a one-to-one correspondence between all the real numbers, the decimal numbers, x, and the points on the number line. Instead, for complex numbers, since we can't order them along a line and keep the field properties, we do the following. We say, well, wait a minute, it's a plus ib and they're both real numbers. So if I put a, I can make a real number line for a, the real part. I can make another real number line b, the imaginary part. And then each point in the plane will correspond, if this is say b0, and this is a0, each point in the plane will correspond to a0 plus ib0, a complex number. So if I go 3 units this way and 1 unit this way, this corresponds to the number minus 3 plus 1i. So we'll put a one-to-one correspondence between the points in the complex plane instead of a one-to-one number between the points on the real number line. So this is the complex z equals a plus ib plane. Each point identifying a unique complex number. Now, with that in mind, we define the absolute value of a real number is its distance from the origin. Maybe we can define the absolute value of a complex number the same way. All right, so for instance, this number at a0 plus b0I, what's its absolute value? Let's make it the distance to the origin right here. And we'll say this is the absolute value of a0 plus ib0. And what is it? Well, it's Pythagorean theorem, right? a0 squared plus b0 squared square root. That's how we'll make the definition then. And then it corresponds to this one. In the special case, you put a point on the real line, the absolute value still holds like it did on the number line there. So the definition is that the absolute value of any number a plus ib is the square root of a squared plus b squared. It's a real number. Absolute value is a distance, so it's a real non-negative number. Sometimes we call this the modulus also. If you hear that term, it means the same thing. Now, how can we identify complex numbers here besides using their plane coordinates A and B? Maybe I remember polar coordinates. I can identify each point in the plane by taking its distance, which is now the absolute value, and its angle, here theta. When we do that, we obtain what we call the polar form of a complex number. So we're going to also let theta, or the argument of a complex number z equals a plus ib, be the angle in standard position from the origin which we can write as just 0 or 0 plus I, either way. Hence, the way you find it, we just refer to polar coordinates. How do we find this angle theta in polar coordinates? Well, we said if you had y and x here, tangent theta was y over x. That's how we define it out of the unit circle, actually. And it doesn't matter what quadrant it's in. It's easiest to draw in the first quadrant. But we know that tangent of theta is, well, y over x is now b over a. And now, just like in polar coordinates, we can identify each point either by a and b, it's the points it projects to on the a and b axes, or by its absolute value and argument. Now, one thing, remember there's two different angles that have this ratio. One of them goes to AB, one of them goes to minus A minus B. Which one shall we use? We have to put it in the correct quadrant. So you demand that theta satisfy tangent theta equals b over a and go into the correct quadrant. And if it's on an axis, the angle is obvious. And now what we have is the following. An analogy, all the polar coordinates we already did. What is this length here? Or what is this displacement? Because it could be negative if we're over here. Well, it's the absolute value of z. I'm going to do this to follow polar coordinates. Let r denote the absolute value of z, as in polar coordinates. And theta denote the argument of z. You get, well, let's see, b over r, we call this r now, and this is b, let's just call this a and b, how about, instead of a0 and b0. So if this is a and b, then this side, this side is the r times the cosine of theta. so that this over this is cosine theta, right? Adjacent over hypotenuse. This side must be our sine theta. It's just like polar coordinates, so that this over this is sine theta. Right? And so we observe that we can convert to the polar form here by finding r, the absolute value of z. Is the square root of a squared plus b squared. And tangent theta equals b over a instead of y over x, with theta in the correct quadrant, the one that goes to the point. And we can go the other direction now too, just like polar coordinates. This converts the standard form or rectangular form, the handout calls it, of a complex number z equals a plus ib to this other form. Evidently, since z equals a plus ib, and a is r cosine theta, and b is r sine theta, we have that any complex number z can be written as, we'll factor out the r times cosine theta plus I sine theta. This is called the polar form of a complex number. When we write it in this form. This gets to be a lot of writing, sometimes cosine plus I sine, cosine plus I sine. A lot of people like to abbreviate it. Pretty much all textbooks put it somewhere just to show you as r psi theta. And this is a definition. R psi theta means r times cosine theta plus I sine theta. This is short notation for it. Okay. So that'll be the polar form. And then this other form, a plus ib, we call the rectangular form or standard form. We need to do some conversions now. Suppose I gave you the complex number z in rectangular form is minus 3 square root 3 plus 3i. How about that complex number? What is its polar form? You might say, why do we need to do this? It's coming up, actually. There's some really neat algebra tricks you can do in the polar form. So what do? We simply say, well, we need to find the number r, which is the absolute value of z, is the square root of a squared plus b squared, the numbers that don't multiply I and do multiply I respectively. So I take minus 3 square root 3 squared plus 3 squared. Now let's see, I get 9 plus 27 is 36. Square root is 6. So this point is exactly 6 units from the origin. And then I solve tangent theta equals b over a is 3 over minus 3 square root 3. How can I do that? Find theta. Well, you simplify it by canceling the 3's, and you say this is actually minus 1 over square root 3, and that looks like it comes from a special angle. If I think about it, I can divide the top and bottom by 2 and write this as minus 1/2 over square root 3 over 2. And now it's a point on the unit circle. And I can do the following. I can go to the unit circle, not the complex plane. This is the unit circle in the xy plane. And I'll plot it. Maybe this is b or y. And this is x. Then y is minus 1/2, halfway down here. X is plus square root 3 over 2, almost all the way over here. It's about that point right there. And I say, maybe my angle theta is this, or I could do it the other way, it doesn't matter. Let's do it the other way just for fun. What angle is that? Well, y is -1/2 and x is square root of 3/2. So this side is 1/2. This side is square root of 3/2. And so this must be a pi/6 angle clockwise is minus pi/6. Is that the polar angle? Maybe. It has to go in the right quadrant. Let's see. A is supposed to be negative and B is supposed to be positive, and they're okay, so this is wrong. It must be that I go over this way. The other thing I can get is +1/2 over minus square root of 3/2. And I scratch out this one because I want to go into quadrant 2 of the complex plane. And now I get this point with y/2 and x square root of 3 over minus square root of 3/2. And I say, well, by symmetry, this angle must be pi/6, since this angle was measured positive. That makes the angle I'm interested in, the angle in standard position of this complex number will be pi back up pi/6. Well, 1 pi minus a 6 pi is 5/6 pi, right? So there's my angle theta. And here's my value of r. R is 6, and theta is 5 pi/6. So by 1, we write the complex number in its polar form. Z equals -3 square root of 3 plus 3i is also expressible as 6 times cosine 5 pi/6 plus I sine 5 pi/6. After all, if you were to multiply this out, this times this, you'd get -3 square root of 3. If you multiplied this times this, you'd get 3. But we call this the polar form because from it you can see the angle on the plane and the radial distance out. So this was the unit circle to find the point, but I can sketch this down the complex plane, the A plus IB plane, and say, well, I just go at an angle of 5 pi/6, and I go out 6 units. This must be where the number Z is, right? All right, so there's converting a complex number from its rectangular form to its polar form. You just find r and theta and write r cosine theta plus r sine theta, or if you prefer, just write 6 psi 5 pi/6. A little shorter. I should mention too that there's another form of this. In higher mathematics, I really prefer this. You can also write this as r e to the I theta, where e is that number 2.718 ... that you learn from finance and so forth. So instead of psi theta, you can write e to the I theta, and e to the I theta for an imaginary unit I turns out to be cosine theta plus I sine theta. But you need calculus to say why. So we won't use this notation here in this class, but be aware if you see a higher class that put r e to the I theta, that's just r times cosine theta plus I sine theta. So I'll just do that for your education. Now, what if we need to convert it back the other way? Then we use our other equations, right? Suppose I said, convert the number in polar form. 12 times cosine pi over 4 plus I sine pi over 4 to rectangular. Oh, this is easy. Really just have to multiply it out, right? We're going to put it into the form A plus IB. Right? What do? Well, I just say Z is equal to 12 times cosine pi over 4 plus I sine pi over 4. All right. Now you remember from the 45, 45, 90 triangle that sine of pi over 4 and cosine pi over 4 are each 1 over square root of 2. And 12 over square root 2 is actually 6 square root 2. If you write this as 6 times square root 2 times square root 2 and cancel one of the square roots. And similarly, this one can be written as square root 2 over 2. If you want to rationalize the denominator, it looks like that. There's the complex number rectangular form, if this is its polar form. Oh, wait a minute. We haven't done division yet. We did multiplication. We did addition and subtraction. And I want to make one note of something that comes up frequently. It's useful, particularly in division, so we'll need it now. If you take the absolute value of any complex number, z given as a plus ib, and you square it, what do you get? Well, the absolute value is square root of a squared plus b squared. That's the way we define it, so it's this distance from the origin. Then we're going to square the square root. We get a squared plus b squared. So a useful identity is to simply write that the absolute value of z, a complex number, a plus ib squared, is a squared plus b squared. If you memorize that, it comes up enough that it actually saves you a little work in doing these things. Now we can do division. To accomplish division, we've actually already got everything we need. We're just going to use the following. We're going to introduce what we call the conjugate of a complex number, and then this will all be easy. The conjugate of z equals a plus ib is z bar we put on there, a minus ib. You just change the imaginary part to minus what it was. That's all there is to a conjugate. Why would we do that? Turns out to be really useful in certain calculations. And with that conjugate, you notice a very interesting thing, that if you take any number z and multiply it by its conjugate, what do you get? You get a plus ib times a minus ib. And you FOIL this out. A times a is a squared, plus this one is minus iab, plus this one is plus iab, and plus this one is minus I squared b. I squared is -1, so a negative and -1 b squared, excuse me. Negative and -1 b squared is plus b squared. These cancel, and I get a squared plus b squared.
Professor?
Yeah.
That's off camera.
Okay.
Thank you.
Yeah. See if I can make you dizzy here trying to move this thing around. All right. So that is any complex number times its conjugate. I put this slash through here so it doesn't look like a 2. Is equal to a squared plus b squared, or the absolute value of z squared. That turns out to be a useful identity. And we're going to use it now.
Hey, Professor.
Yeah.
I have a question about the problem we did just before this one up for polar to regular or standard complex form.
Yeah.
If you can move the camera over there, shouldn't the 12 go to both the cosine and to the isine instead of just to the cosine?
I forgot to multiply it, didn't I? 6 times. Yeah. This is. Yeah. This is. 6 square root 2 plus I 6 square root 2. Thank you. Yeah. The 12 multiplies both of them. I forgot to put my parentheses. This is one thing. happens on exams a lot. I'll say you guys forget to put your parentheses in. Then at the next step, you'll forget to multiply and it'll come out with the wrong answer. Thank you so much. Yeah, so it should be 6 square root 2 plus I 6 square root 2. All right, now, I should say this is an analogy to what you did before. If this seems kind of strange, why would you want to do this? It's to get these things to cancel. This has analogy to what we did before. If we had a plus b square root c, what do we call its conjugate? We just took a minus b square root c. And why did we do that? Because if we multiply them, we got a squared minus ab square root c plus ab square root c plus minus this, minus b squared c, and these cancel out, and we got a squared minus b squared c. The roots went away, and so we call these conjugates. Similarly here, when you multiply a complex number by its conjugate, the imaginary part goes away. So what you get here is the real number, right? A real number squared plus a real number squared, or the absolute value squared. So z times its conjugate is the real number that's a squared plus b squared. And has this analogy of what you did with radicals. It gets rid of the bad part. All right. Now the division. To accomplish division, you do the following. Just multiply the top and bottom, the numerator and denominator. Those are longer words, so let's say top and bottom. By of z1 over z2, that's the division you're going to do, by the conjugate of the bottom. And then it all just comes out. Here's how it works. Let me take it back to the other side. Suppose I wanted to take 5 minus 2i and divide it by 3 plus 4i. How can I do that division? Well, I say that it has to be the same number as when I multiply the top and bottom by the conjugate of the bottom. The conjugate of 3 plus 4i is 3 minus 4i. By the way, then the conjugate of 3 minus 4i is 3 plus 4i. We can say they're conjugates of each other. So we multiply top and bottom by the same thing, the conjugate of the denominator. And now the bottom by our rule over here is just 3 squared plus 4 squared. That's easy. You don't have to do the computation. You can. It doesn't hurt to FOIL it out. It's just extra work. But once you've done a few of these, say, oh, it's just 3 squared plus 4 squared, a squared plus b squared. The top, however, not so. These are its conjugates. I have to multiply them out. 5 times 3 is 15. Minus 20 times I is the outside. Minus 6i is the inside. And the last is minus 2 times minus 4 is 8, multiplying I squared. Well, we will call that I squared is negative 1. And so this is 15 minus 8 is 7. Plus minus 20i minus 6i is minus 26i. All over 16 and 9 is 25. And we observe just by using conjugates that this complex number has to be this one. Well, we know how to do this. Let's break it up into pieces. We'll write this as 7/25 minus 26/25 I. There's the rectangular form of the number. That's the quotient of these two numbers. So the quotient of two complex numbers is another complex number that you get by multiplying top and bottom by the conjugate. That's getting a little trickier, isn't it? Well, if that's not tricky enough, we'll add a new one to it. There's a theorem that says these behave really in a nice graphical way if you put them in polar form. for two complex numbers, Z1 equals R1 cosine plus I sine theta 1, and Z2 some number R2 times cosine plus I sine theta 2. This induces, or this gives, the following results from multiplication and division. If I take Z1 times Z2, what happens? Well, I'm taking R cosine plus I sine theta 1, R1 cosine plus I sine theta 1 times R2 cosine plus I sine theta 2. And I'm multiplying in the order, so I'll just multiply R1 times R2. And then cosine plus I sine theta 1 plus times cosine plus I sine of theta 2 turns out to be, and I'm going to omit the proof on this one, so somebody really wants to see it. It's a trigonometry proof. Remember all those sections we did on proofs? You can do one of those proofs, your sum of difference angles, and say this actually turns out to be cosine plus I sine of theta 1 plus theta 2. So by trig identities, it's not too hard to show. I think I'll skip over for lack of time today. It's not trivial either way to do it. But when you multiply this one times this one, the angles add. And so this is the result. And then also if you take Z1 divided by Z2 in the polar form, you've got R1 cosine plus I sine theta 1 over R2 cosine plus I sine theta 2. Well, R1 over R2 carries through. So the radial distance of any number is the quotient of these radii. And the quotient of these two causes the angles to subtract, again by trig identity. This is cosine of theta 1 minus theta 2. That is the product of two numbers, Z1 and Z2, given in polar form, has a radius that's the product of the two radii of the individual numbers, and a polar angle is the sum of the two polar angles. If I divide them, you get a number whose radius, or distance from the origin, is R1 divided by R2, and whose angle is the difference of the angles. So that's the outline of the proof there, and put in the details. Let's do a simple example here. Suppose I have these two numbers in polar form. Z1 is 2 times cosine plus I sine pi over 3. And Z2 is 1 times, so you can leave the 1 out if you want, cosine plus I sine pi over 4. What is Z1 times Z2 in polar form? Well, you multiply the r's, it's 2 times 1. And you add the angles, cosine plus I sine of pi over 3 plus pi over 4. And I can sketch this pretty readily. All I have to do is go 2 units out at this angle, which is 7 pi over 12 if you do your fractions. And what I have is this. The first one was 2 units out at an angle of pi over 3 like that. That's C1. The second one was 1 unit out, half that distance. At an angle of pi over 4. Now the product I got just by turning to an angle 7 pi over 12. 6 pi over 12 is pi over 2, so it's 1/12 pi past there. Goes in that direction. It has is also 2 units out, so it should be the same distance as that one. And this one right here is Z1 times Z2. It's at this angle 7 pi over 12, 2 units out. So it makes for a nice sketch that you can do with these things. Now the division, we can accomplish similarly. We divide Z1 by Z2. We now have 2 over 1. Actually, let's do the other way. Let's do Z2 over Z1. What I originally intended. Take this one, divided by this one. Then I have 1 over 2, cosine plus I sine, pi over 4 minus pi over 3. Well, this is 3 pi over 12 minus 4 pi over 12 is minus pi over 12. And so you can sketch the quotient by going an angle minus pi over 12. Very small angle, half, about 15 degrees. And just go out 1/2 unit. I should draw this dotted out here. So this is dotted to show the angle. And we're about right here, 1/2 unit out. Z2 divided by Z1. Right there. 1/2 a unit out in this direction. So it's real nice for drawing these things. You know, the polar form of these complex numbers. Furthermore, this leads to some interesting theorems. Including de Moivre's theorem or de Moivre's theorem, depending on your pronunciation. It says this, that if you take a complex number in its polar form, r times cosine plus I sine theta, to the nth power, what you get is the radius of the nth power of the original radius times cosine plus I sine of n times the angle. You might be able to see the proof of that one from the multiplication theorem I just did. I'll put reason because I'll put part of the proof in here, most of it actually. Right, if you take r cosine plus I sine theta to the nth power, then you've got n of those multiplied together. R size theta, n of them. Now you can multiply in any order, so n r's multiplied together is r to the n, where r is a real number, recall. It's the radius, the distance from the origin, the absolute value of z. And then when you multiply cosine plus I sine theta times cosine plus I sine theta, the angle adds, you multiply 2 of these, you get 2 theta. Multiply 3 of them, you get 3 theta. Multiply 4 of them, you get 4 theta. They just keep adding and adding. If you multiply n of them, you're just adding theta n times, and you get n theta. Right? So the angles add theta plus theta n times, and these multiply, and the radii multiplied n times, so you get n r's all multiplied together here. So that verifies de Moivre's theorem. And this tells you a nice way to take powers of complex numbers. You can see the trigonometry coming out of this, right? Angles in standard position. You can plot all these things. Find my page here. Here's an example of the problem set. This is number 6A. Suppose I wanted to take the 5th power of minus 1 plus I. I wonder what it is. You can multiply that together, five of them, and have a big chance of mistake. If I put 50th power, you'd be sure to make a mistake, right? But using de Moivre's theorem, we call it equation 2 or something. By equation 2, tells you exactly what to do. You rewrite this first in its polar form. Just to put this in the next step. Well, what is r? Right, just like in polar coordinates, it's a squared plus b squared. So you think of this as minus 1 plus I minus 1 plus 1 times I. So the imaginary part is 1. To take r squared plus 1 squared square root. Be careful, don't square I and get 1 minus 1. That's incorrect. It's a squared plus b squared, where b is the number that multiplies I, not I. Right? So it's minus 1 squared plus 1 squared square root is square root 2. That's the distance you are from the origin of the complex plane. And then tangent theta has to be b over a is 1 over minus 1, which you can write as 1 over square root 2 over minus 1 over square root 2. As you go sketch that in the unit circle with y and x, then x is negative out here minus 0.7, and y is positive out plus 0.7. Goes into the same quadrant as this one, a negative and b positive. And what angle is that? Well, you can figure it already since they're equal with it. Right, the point on the unit circle here, it has 1 over square root 2 this direction, but negative, and 1 over square root 2 this direction, positive. It must be that this is a 45, 45, 90 triangle, which makes this angle in standard position, theta, the argument, equal to pi, back up pi over 4. Pi minus a fourth pi is 3/4 pi. Almost off the screen there. And so I know the angle is 3/4 pi and the radius is square root 2. So I rewrite this as square root 2 times cosine plus I sine 3 pi over 4. And I'm going to take that to the 5th power. Now, by equation 2, I'll say this is your r, this is your theta. You take r to the 5th, square root 2 to the 5th, times cosine plus I sine 5 times the angle that you have. So r to the 5th, cosine plus I sine 5 times theta. And now it comes out to be, let's see, 2 of these make 2, another 2 make 4, so I got 4 square root 2 here. And this one is cosine plus I sine 15 pi over 4. Maybe I'll get rid of this short notation to figure out what the actual rectangular coordinates are. It's 4 square root 2 times cosine 15 pi over 4 plus I sine 15 pi over 4. I just got to figure out where that is. Again, run to the unit circle. 16 pi over 4 would be 4 pi, right? That'd be 2 times around. So it'd be like that. There's 16 pi over 4, but I've got one less. It's going to be 15 pi over 4, so now I go minus pi over 4. And I go in that direction. This one here, almost 2 times around, would be 15 pi over 4. So I dropped the perpendicular here, and I noticed, should have drawn that a little better. It's split the axes here. It should be halfway between. And now I drop the perpendicular. This is a 45, 45, 90 triangle. This length is 1 over square root 2, and this length is 1 over square root 2. I observed that cosine and sine, respectively, are the coordinates 1 over square root 2 and minus 1 over square root 2. That's the cosine of 15 pi over 4 and the sine of 15 pi over 4. So I put those in. The 5th power here is 4 square root 2 times cosine is 1 over square root 2 plus I sine is minus 1 over square root 2. And now the square root 2's cancel, and I get 4 here, and minus 4i here. So there's the fifth power. If I put it into its polar form, all I have to do is add multiply. I don't have to FOIL a whole bunch of times. If I had 50th power, I could need this. Maybe I'll put that in the test. Okay, so there's calculating a power of a complex number. You could figure this out from its polar form too. Just have to figure out, rotate around 15 pi over 4, takes you all the way around like this, and then go out 4 square root 2 units. And you can figure it out. This triangle must have sides 4 and 4, and say, oh, this is just 4 minus 4i, and you can do it that way too by sketching it. Go out 4 square root 2 units, at an angle 45 sort of a second rotation, and you can get it from the triangle too if you like. So sometimes there's a preferred way that you like that works easier for you. You're welcome to do that. Well, the last and hardest topic, in fact, it's the only real hard topic today, is roots of a complex number. This polar form is really useful for finding roots. Most semesters, I don't even get to this. You guys are lucky. Probably because you're not here to slow me down so much. I'm going faster. I thought when I first started teaching that I would get faster and faster at it as I practiced more. But what happened is that the more I did this, the more I had more things to say, and I took longer and slower. But somehow this semester I actually sped up a little bit because you're not asking questions so much. All right. So here's roots of a complex number. Similarly to De Moivre's theorem, if you want r cosine plus I sine theta nth root, so I'll write it as 1 over n power. One of those I can figure out by De Moivre's theorem, right? If I take r to the 1 over n and cosine plus I sine theta over n, if I think about it, taking the nth power of this gives me this number inside the parentheses, right? Because I take the nth power of this, it's the nth power of the nth root, I just get r. Here, when I take the nth power here, it's cosine plus I sine. You add all the angles, you add theta over n times, and you get theta. You add this n times, you get theta. You multiply this n times, you get r. Voila, right? This is a root, but it turns out when you have nth roots of a complex number, there are actually n different ones. How can we get that? This is just one of them. Here's how you can get the others. Remember, cosine and sine are both 2 pi periodic, so if I add to this 2k pi for any integer k, right? 0, 1, minus 1, 2, minus 2, etc. This will be the same number, right? Because cosine and I sine will have the same value. I guess I should put it over here. Replace theta with theta plus 2k pi. This will have the same value. Multiply times r will have the same value. If this is the same complex number, then this is also a root of r size theta. So, in fact, all the numbers that multiply out n times to give r size theta are these. Theta plus 2k pi, where k equals any integer. Well, that sounds like an infinite number of solutions, right? Because it can be any integer. But what happens, however, is if you start with k equals 0, you get one complex number. That's the first one, theta over n. You do another, if we put k equals 1, you get another complex number, theta plus 2 pi over n. K equals 2, you get another one, theta plus 4 pi over n, theta plus 6 pi over n. And you keep going up to n minus 1. But then when you put k equals n, you get theta plus 2n pi over n. Well, theta plus, if this is 2n pi over n, The ends cancel and you get plus 2 pi is the same value plus for cosine plus I sine is the same complex number. So you actually only get different complex numbers for k running from 0 to n minus 1. And after that, you get the same ones. So these are all the different complex numbers whose nth power is the complex number with polar form r psi theta. We could call that equation 3, I guess. That's how you find the nth roots, is you make this computation. And you get n roots. And different numbers. When you take an nth root of a complex number, there's n different numbers in a complex plane, all of whom, when you take their nth power, give you this thing. All right, so let's apply formula 3 to find some nth roots. And these have a really beautiful diagram, even though, like I say, they're kind of tricky. Suppose I want to take the cube root of 64 times cosine plus I sine of 3 pi over 4. I'm going to take the cube root. How many of those are there? It's cube root, there's 3 of them, right? So we expect to get 3 complex numbers, each of whose cube is this number. Kind of stuff is fairly easy when you start, but when you start building and building, it starts to get tricky. Well, by our theorem, 3, we have, this is 64 to the 1/3. We take the 1/3 power of the radius, and we take 1/3 of the angle. So, third root of this, and 1/3 of the angle. And we can also add 2k pi up here. And we let k be 0, 1, and 2 when n equals 3 is the root. So by formula 3, these are the 3 roots of the number 64 size 3 pi over 4. By the way, you can figure out what this is, rectangular coordinates. If you convert that to rectangular coordinates, you're going out 64 units at an angle of 3 pi over 4. All right. This is just 64 over square root 2 and 64 over square root 2. So the number we're doing in here is 32 square root 2 I, 32 square root 2 plus I, minus 32 square root 2 plus 32 square root 2 I. That's the number we're taking the cube root of. Cube roots. Well, this means take the cube root of the real number. There's only one answer here. What times itself 3 times gives 64? 4 times 4 times 4. So this one is 4. You can do it on your calculator if you want. All right. And now, how about this? If I divide 3 pi over 4 by 3, I just get pi over 4. And then I've got plus 2 thirds pi times k. I divide this one by 3. So the 3 roots are, and this is k equals 0, 1, 2, 4 cosine plus I sine pi over 4. That's when k equals 0. When k equals 1, I get 4 cosine plus I sine this plus 2 pi over 3. And then 4 plus twice that. 4 times psi pi over 4 plus 4 pi over 3. There's the polar form of the 3 complex numbers that have this power. I think on the homework problems, they just said find the answers in polar form. We already showed how to convert the polar form to rectangular coordinates. Yeah, since the homework is just asking you to leave these in polar form, I'll just leave it like that. I guess we should add the angles together to find out what the actual angles are. So in polar form, three roots are 4 cosine pi over 4 plus I sine pi over 4, or you use the shorter notation, I don't care. 4 times, well, let's see, this is 8 pi over 12 plus 3 pi over 12 is 11 pi over 12. So it's cosine 11 pi over 12 plus I sine 11 pi over 12. And then the last one, let's see, this is 16 pi over 12 plus 3 pi over 12 is 19 pi over 12. Or cosine 19 pi over 12 plus I sine 19 pi over 12. So there's the polar form of the three complex cube roots of 64 size 3 pi over 4. Just take the third root of the original radius and divide the original angle by 3 and add 2k pi over 3 to it. This one isn't too hard to figure out, right? This part is 1 over square root 2 for cosine and 1 over square root 2 for sine. So if you wanted to put this one into rectangular form, it's 4 times 1 over square root 2 is 2 square root 2 plus I times 4 over square root 2 is again 2 square root 2. So this is the first root here, and you can do the same thing for the others. You want to put them in rectangular form. The neat thing is the picture that goes with it. You don't have to draw the picture, the homework doesn't say that, but this picture makes it so memorable. Here's what I do. If I'm out at an angle of 3 pi over 4, that's what this original thing is. It's 3/4 of pi, it's 3/4 turned to a straight angle. And I go out 64 units. All right, here's my original z equals 64 cosine plus I sine 3 pi over 4. Right? That's why I plot that complex number at this angle and that distance. Now, what are the cube roots? Well, I take the cube root of the distance, which is 4, a little tiny number, and I start off at this angle, pi over 4, right here. Four units out. And then the other two are just symmetrically displaced. The next one is right here at an angle of 11 pi over 12. And the next one is symmetrically displaced here at 19 pi over 12. So we got, and also 4 units out. So the three roots of 64 cosine plus I sine 3 pi over 4 all lie on a circle in the complex plane. This is the complex A plus IB plane of radius 4. The cube root of the radius of the original circle with this one. So that's what you do here. Geometrically, if you think of 64 size 3 pi over 4 as lying on a circle of radius 64, you take the cube root of the radius, which is 4, and then you turn through 1/3 of the angle. That is 1, 2, 3. You take 1/3 of the angle for the first one, and then you place the other two symmetrically around. 2 pi over 3 around, 2 pi over 3 around, another 2 pi over 3 around. Takes you back where you started. So these are the three roots here, here, and here on a circle of radius 4. So that's the nice sketch of what's happening geometrically. So as you can see, trigonometry does a nice job of helping you visualize complex numbers and make some of these cube root calculations, well, any root calculations. Take a 4th root or a 5th root, or if we're doing powers, the Miles theorem, same thing. Any questions you want to look at based on that? I'm going to try one more then. This is off the last problem here. This is number 7. B, let's say. Suppose I take z equals, well, let's say 5, the cube roots again of -16 plus 16 square root 3.
Professor?
Yeah, I'm off the screen, right? Yeah.
Thank you.
Suppose I want the cube roots of this number. I'm going to start with it in rectangular form this time instead of polar form. What's the first thing I do? I just put it in the polar form. So I calculate r for this number is the root sum square of the component of the real imaginary part. So it's minus 16 squared plus, oops, I forgot this I in here. Minus 16 plus I, 16 square root 3, cube root. All right, so plus 16 square root 3 without the I squared. And let's see, I've got 256 here. And 3 times 256 here makes 1,024 total. Square root of 1,024 is 32. This is for all you computer science buffs, actually. How do I figure that out so quickly? You memorize those powers of 2. 2 to the first, 2 to the second, 2 to the third, right? If you get up to 2 to the 10th, that's 1,024. We call that 1 kilobyte of memory when you have 1,024 bytes. So kilometer refers to 1,000 meters, but kilobyte refers not to 1,000 bytes, but 1,024 bytes. So it's a power of 2. You get used to memorizing those things for computer science purposes. Then when you take something like this, I mean, 16 is 2 to the 4th. Take that to the second power, have 2 to the 8th is comes out to be 256. You just memorize these powers. 256, 512, 1,024. And then you've got 256 plus 3 times, that makes 4 times 256, 1,024. And that's kind of fast, but once you memorize these powers of 2 through 1,024, they come fairly easily. So there's R. Now what's theta? I can sketch this in the complex plane and say tangent theta is B over A. It's 16 square root 3 over minus 16 is minus square root 3, which I can then write again suggestively as minus square root 3 over 2 over a half, or square root 3 over 2 over minus a half. Either way, which quadrant do I want? I want A negative and B positive, so I want this one. This is B over A, right? Or Y over X. So I throw that one out and I put it in quadrant 2. And now if Y is square root 3 over 2 on the unit circle, and X is minus a half on the unit circle, what we have is a point like that that's at 2 pi over 3. So evidently the angle is 2 pi over 3. And the radius is 32. So I'll rewrite this as 32 cosine plus I sine of 2 pi over 3. And I want to take the cube roots of that this time. How do I do that? Well, it's cube root of 32 times cosine plus I sine of the angle plus 2k pi. Divided by 3. Well, let's see, it's 32 to the 1/3. Well, this is 2 to the 5th power, so third root isn't going to do much for me. I can take it as cube root of 8 is 2, and then that's times 4 to the 1/3. I write 32 this way, 2 times 4 to the 1/3. You want? And then this one is cosine plus I sine of 2 pi over 9, dividing the first part by 3, plus 2 k pi over 3. Those are the 3 complex numbers. That are cube roots of 16 minus 16 plus I 16 square root 3. So I have then, in polar form, they are 2 times 4 to the 1/3. If I put k equals 0, I just get cosine plus I sine of 2 pi over 9. So there's the polar form, or you write size if you like, doesn't matter. Of the first 0, then the second one I put k equals 1. this is k equals 0 in equation 3. K equals 1 adds 2 pi over 3 times 1. So I get 2 pi over 3 plus 2 pi over 9. Right? Gives me, let's say, it's 6 pi over 9 plus 2 pi is 8 pi over 9. So this is now 2 times 4 to the 1/3. Cosine 8 pi over 9 plus I sine 8 pi over 9. And the last one, I add 2 pi over 3 again. So I get 2 pi over 9 plus twice 2 pi over 3 is 4 pi over 3. That's k equals 2. And let's see, this is 12 ninths plus 2 ninths is 14 ninths. So the last one is 2 times 4 to the 1/3 times cosine 14 ninths pi plus I sine 14 pi over 9. There's the polar form of the 3 complex roots, and you can multiply this out and see what the rectangular form. Let's leave it there. Try all the, for homework, try all of the problems on the UCO supplement, all of 8.5 on complex numbers. Here's what I'm going to do for the final exam if you want to study for it. The practice problems are already out on D2L. You can download those. On the final, I'm going to make it short. I'm going to make it just like the, you have an hour and 50 minutes to do it still, but I'm just going to give you problems about the length of the regular midterms. It counts the same as the midterms, and it's taking me so long to grade these things. I'm worried I won't finish them in time for the deadline. So I'll make it take you about an hour and a quarter, but you can have the whole hour and 50 minutes. And I'll make all problems similar to the practice problems if they're from before, if they're material from before the last exam. And then I'll say any homework plus the practice problems or material we've done since the last exam, which isn't much actually, right? We just done some applications. We did polar coordinates, vectors, and complex numbers. Those 3 topics I ask you things out of the homework and the handout. Otherwise, it'll just be the handout, the practice problems. Well, thank you for attending this morning. Hope you had a good semester. Bring me some questions next time.
Thank you.
Thank you.